Hello, this will be the part 2 of the chapter 4 video, and we left off with this map right here. What we will take off from here is now trying to apply some of our concepts of how to use understanding isobars and how to read weather maps and wind directions. One of the things, again, I would ask you to do is really great resources on YouTube, how isobar maps are created and read. A nice little search for YouTube videos on that topic would really help your understanding of how a map like this is constructed and how you use it. So it's a search string like "what are isobar maps" or something along those lines would be nice little 5 to 8 minute tutorial. Would really be helpful for you to understand a map like this and be able to answer questions later. If you're a visual learner, I would highly recommend you to do that. Moving on, our key understanding is to kind of putting together 3 or 4 processes of how winds are created and what kind of initiates them to go. And we're going to talk about really phase 1 or step 1 is this thing called the pressure gradient. The pressure gradient is sort of like when you press the gas pedal on your car. It's what makes your car go forward. It's what initiates air motion, and we typically see air motion moving from high to low pressure. And the map of isobars is what really tells us how fast the air is moving and what from direction. And generally in weather forecasting and trying to predict weather, if you know how fast the air is coming and from what direction, you really can gather a lot of predictive analysis on what the weather is going to be like down the road. So we're going to talk about horizontal and vertical pressure gradients here in a second, and it'll be very interesting to kind of compare the difference between horizontal pressure gradients versus vertical, and I'll try to give some examples and comparisons of how they're similar and different. This is an example of a horizontal surface pressure map. You've seen this map before, and horizontal pressure gradients typically are quite slow in terms of how fast air pressure changes. And so when we look over the United States and we look at the change in horizontally, horizontal means how air pressure is changing as you move and walk across the earth, and as long as it's fairly flat, you're basically walking horizontally over the earth. Air pressure on this map changes from a maximum of 1020 over the southwest and goes to a minimum of around 980. That means the highest and lowest air pressure changes about 30 millibar over the entire United States. So that's actually quite small when you consider the millions of square miles. When we start talking about vertical pressure gradients, we can go from 1,000 millibar to 500 millibar in 5 miles of vertical altitude. So when we talk about like flying in an airplane and going up through the atmosphere, that would be more of an example like a pilot would be really interested in vertical pressure gradients. And they change very rapidly. So again, maps like this are what we tend to spend more time looking at as horizontal pressure gradients. And we'll look at some examples here in a second, and we'll probably spend more time on horizontal pressure gradients, but we will see some examples of some vertical pressure gradients as well. I'm not going to talk so much about the hydrostatic equilibrium, very complicated, but we will get into some of the idea of how density affects air pressure. And when we talk about air temperatures, we'll get into some visual examples here in a second of how does air temperature affect the density of the air, and ultimately the air pressure readings in millibars or inches of mercury that we look on some of our later maps. But we're not going to spend a great deal of time on these terms right here. We're going to look at some more common lay terms that I think will make more sense to you. The key thing that we want to understand about pressure gradients is that if we have 2 columns of air, that effectively they probably will have the same air pressure on the ground as they would above them. So we would say that the molecules have the same amount of kinetic energy, and the density of the air would be about exactly the same if the 2 columns of air were about the same temperature. However, unlike our earlier example with the ideal gas law, when we go outside, the air does expand or compress. There is no magical lid on it. And what would happen is if we heated one column, it would actually rise and expand. And what would happen is we would spread more molecules. We would make them move faster, and as they move faster, they would spread out and expand to cover a greater volume. And as a result, as we heat the air, it actually creates lower density. And that ultimately creates less dense air on the ground, whereas cooler air causes molecules to get closer together and creates a greater density and actually creates higher pressure. So if this was a weather map or a slide on your notes, I would actually put an H under the cool column and put an L under the warm column, because warming air causes air to expand, and inevitably what that does is it actually causes higher pressure in the upper atmosphere, because all the molecules near the ground are being forced up to higher levels. And often in the upper atmosphere, we actually see higher pressure in the upper atmosphere above a warm column, and lower pressure at the surface, and vice versa. On the ground, we see, under a cold column, we see H's and we see L's, because all the molecules are sinking towards the ground. So what we end up having is an H, an L, H, and an L, and we end up getting a circulation pattern that moves just like this. If you're following my cursor, it creates a circulation pattern. And you could almost imagine this is what structures winds to move over the Earth, as the warm column really represents the equator and the cold column represents the poles. Basically, the distribution of high and low pressure surface in the upper atmosphere creates currents of air that are basically recirculating heat between the equator to the poles to balance out the differences in temperature. So horizontal pressure gradients in the upper atmosphere become to be important because they really begin to show how the atmosphere is connected three-dimensionally. And so I'm going to go straight to the map to show you. We often look at what's called the 500 millibar surface. And under the 500 millibar surface, we can look at the altitudes, and the numbers on this map here over Cuba say 588. Here they say over southern Texas 582, 576, 570, 564, 558. All these numbers are altitude readings, and they're missing a zero. So this actually is not 582, it's 5,820 height contour. And what this tells us is that as you look and go further north, the numbers are increasingly getting smaller or lower in altitude. So for example, over Quebec or New Brunswick, Canada here, you could actually see the number is 528. So the 500 millibar height, that's about half of sea level pressure. And the altitude over Cuba is 5,880 meters, and the height of the 500 millibar surface over northeast Canada here is 5,280 meters. The difference in this is because the air over the southern states is warmer, and the air is expanding and becoming less dense. So the upper level winds really want to go from south to north because they're transferring warm air to cold air in the upper atmosphere. And this becomes a very important concept, that we realize that all these air pressure surfaces are either compressing or expanding, are creating winds to try to transfer cold and warm air to balance out the differences of heat and air pressure across the Earth. So here's a better example of it. Is the 500 millibar height over southern Mexico is 5,600 meters. Over the Canadian-American border, it's 5,500 meters, and over northern Canada and central Alaska, it's 5,400 meters. Again, this is a good example to show you how in the upper atmosphere, air is expanding over the southern parts of the Earth towards the equator, and the air is compressing. It's this compressing air and expanding air that's creating pressure gradients over the entire Earth, and what effectively is creating wind. If effectively Mexico and northern Canada were the same temperature, we would not see these differences, and we wouldn't really have wind moving across the Earth. So when Canada and Mexico get closer to the same temperature or the same temperature, we would no longer see winds moving across the Earth and creating weather like we see today. So now that you understand the pressure gradient, there are forces that actually affect wind directions. Pressure gradient is what it creates wind speed and direction, or wind speed, but we do have forces that can alter the direction. The reality is as winds are moving across the Earth is also spinning and rotating. And the Earth's rotational force is called Coriolis. Coriolis force doesn't create wind, but it certainly modifies its direction. I often talk about in class, the Coriolis force is sort of like a steering wheel in a car. Your steering wheel doesn't cause your car to go forward, but it certainly can influence its direction. And so the Coriolis force has differing degrees of impact because the Earth spins at different rotational speeds. That's what creates the Coriolis force. So at the equator, the Earth spins the fastest, and at the poles, the Earth spins the least. In fact, at the North and South Pole, there is technically no rotational speed. So the further you go away from the equator, the Earth's rotational speed changes and gets less. That's what effectively causes winds to deflect. And the best example is often a merry-go-round. And generally, this example here shows you a merry-go-round spinning, and the Earth rotates counterclockwise. And there's great examples on YouTube of how the Coriolis works, how the Coriolis force works. You can find some excellent videos on that topic. But the net effect is because of the net change in rotational speed, when winds move in the northern hemisphere, they tend to deflect to the right, and in the southern hemisphere, they tend to deflect to the left. And there's many technical reasons and definitions of why it goes into right and left. But I think the best way for you to learn those technical issues would probably to be watch a YouTube video. And I do post some videos under Chapter 4 about the Coriolis force. But for now, we understand that the pressure gradient can send the air in one direction, but in the northern hemisphere, the Coriolis force wants those winds to turn to the right in the northern hemisphere, and the pressure gradient force gets deflected to the left in the southern hemisphere. Friction basically operates like a set of brakes on a car. Friction basically works in direct opposition to your gas pedal, and it's what slows air down. So things like buildings, mountains, large trees, they effectively operate to slow winds down and effectively stop winds from moving over the Earth as best they can. So the net effect of friction is they effectively slow winds down almost to a halt. And so when we talk about winds moving over the Earth, we effectively have three forces: pressure gradient forces winds to go forward. Coriolis force tries to deflect winds to move to the right, and Coriolis force tries to move the winds to the right, and friction tries to act to slow the winds and stop the winds from moving altogether. These factors together are what shape and influence wind speeds and directions all over the planet, and it's them three working together. And I think this represents a good point to stop, because we will finish with a part 3 so you could see how all three of these forces work together to influence wind speeds and directions for surface winds versus upper level winds on the last half or the last part of the chapter 4.